Hello all. So this is the video solution to the numerical exercises of the first homework. So this numerical exercise covers using the libraries NumPy and Matplotlib, using vectors, matrices, and various calculations with those objects in Python, and then analyzing data and graphing it. So this is the notebook Morton has released as the solution, and I just want to walk you through the different code cells here and explain what they do. This first code cell here simply imports the library NumPy and the library Matplotlib. NumPy is used a lot to make vectors, matrices, and do various calculations with those, while Matplotlib is used a lot for graphing. You'll get a lot of practice using these two libraries in this class, and if you're not familiar with them, I suggest you look up some tutorials online or you ask a member of the teaching staff because you'll be using these a lot. So the first 5 exercises use the NumPy library to do various calculations with vectors and with matrices. And we start out with looking at some vector calculations. So this code cell here simply defines a NumPy array with 3 elements in it. In physics, this is going to correspond to a vector of length 3. So this code cell here simply defines 2 different vectors, each of length 3, and then it prints the contents of each vector. If you're not familiar with using NumPy arrays, there's a helpful link here in the solutions notebook, and you can also take a look at the introductory lecture slides. We'll be using NumPy arrays a lot in this class. So these first 4 homework questions simply want you to do some simple calculations with the NumPy vectors and then check the results by hand. So the first 2 calculations simply want you to subtract vector 1 minus vector 2, and then vector 2 minus vector 3. So you can do that as simple as you would a subtraction for any other variable in Python. You just type the name of your first variable, a minus sign, and then the name of your second variable. So this is the solution for part A, and this is the solution for part B. And if you like, you can go back through and double check these 2 lines by hand to make sure they're correct. Part C of this problem wants you to do the dot product. So there are 2 ways to do this. The way I prefer is this first way up here. So you type the name of your first vector, dot, the word dot, and then in parentheses your second vector. So what that does is it tells NumPy to do the dot product of v1 and v2. And you get 32, which you can check by hand if you like. A second way to do the dot product in Python is to do the @ symbol in between the 2 vectors. This gives you the exact same answer, but I find that it's sort of less intuitive and it's not as easy to just read off what the code is doing. The last thing this code asks you to do, which is not included in this notebook, is to find the dot product of the 2 vectors. So again, there's a couple ways to do this. One of them would be to write your own function to find the cross product. You could write your own function to find the cross product, but a really simple way would just be to use a built-in function in the NumPy library. So if I define a variable called cross product to hold the result, finding the cross product is as simple as typing np, which stands for NumPy, dot cross, parentheses, and the name of my variables. And that will just compute the cross product. So there's a small challenge here to write your own function to find the dot product. I'm not going to cover this in the video solution, but if you have any questions about that, please contact me and I'll be happy to go through it with you. So the next part of this notebook walks you through setting up matrices in Python. So there are sort of 2 ways to do matrices here. You can use the np.matrix function and simply list them here as kind of like a 2D array. Another way is you can use the exact same syntax, but instead of matrix, type array. So in this case, this would be a 2D array. Both of these are valid, and you can use whichever one you feel more comfortable with. And so you can add them the same way you would any other variables, just with a plus sign. You can subtract them with a minus sign, that sort of thing. And there's also a bunch of built-in linear algebra functions in NumPy that you can look through if you like. If you're ever asked to do anything with a matrix, such as take the inverse or the transpose or multiply two matrices, it's very, very likely that NumPy has a built-in method for that, and you should do a quick Google search to make sure. So question E here wants you to take the rotation matrix that was defined in part 6 of this homework and actually code it in to rotate this vector by 45 degrees. And so the homework gave you this sort of starter code where it defines a random vector of length n and a random 3x3 matrix, and then it takes the dot product of those two. So this is a good starting point, but we need to replace A and R with what they actually stand for. So going down to this code block here, A, as in the problem statement, is simply a vector with components 1, 0, and 0. So that's pretty easy. So now moving on to the rotation matrix. First, to define the angle. So if you're going to use the built-in sine cosine functions either in the math library, which is what the solution uses, or in the NumPy library, they expect the input to be in radians. So if you're given an angle in degrees, to use it in these Python codes, you need to convert it to radians. So to do that, you simply multiply by pi and divide by 180. So after defining the angle in radians, you can compute the cosine of the angle using the built-in function from the math library. And then you can define the sine of the angle. And then finally, going forward, you can define a 2D array or a matrix, depending on which one you prefer, with this being the first row, this being the second row, and this being the third row. And if you go back and look at the rotation matrix from part 6, that should match it exactly. So now that we've defined A and we've defined R, we can do the matrix multiplication here and see that this is in fact a rotation by 45 degrees around the z-axis. So that's all we wanted to cover with vectors and matrices. If you still have questions, please feel free to ask us because you'll be using these a lot. And it's good to get any kinks worked out early in the class. So moving on to the last part here. The last part wants you to analyze this data and do some calculations with it. So this data gives you the x position of the runner Usain Bolt at different times. And from this data, you need to calculate the mean velocity, the total velocity, the mean acceleration, and the total acceleration. And I'll go through what those mean. So the first step here is simply take the data given in this chart and put it into NumPy arrays so it's easier to manipulate. So we call the x data x and the time data t. And given these two arrays, you can plot them using the matplotlib function plot. So the syntax here is pretty easy. The first argument is the x data. The second argument is the y data. So what you want to plot on the x is first, what you want to plot on the y is second. And if you like, you can do cosmetic things like change the color or change the line style, but that's not necessary. Since this is physics and the x and the y-axis typically mean things, you want to add labels. So for example, we add the x label with plt.x label. And on the x-axis is time, and it's usually helpful to put the units. And then you add the y label in a similar way, just plt.y label. A title to the graph is optional, but it is helpful to be able to read the title that quickly tells you what the graph is about. And this plt.show function is optional. If you're using a Jupyter notebook, the graph's going to come up whether or not you have it. But if you're writing code in a Python file, you have to have the show statement in order for the graph to show when you run the code. So first, let's calculate the average velocity and the total velocity. So those words are a little bit confusing, I understand this. So let me see if I can help clear up the confusion. So average velocity means the velocity between the current time interval and the previous one. So if I was writing this out in code, I would take cycle through every time interval between 1 and n. So by intervals, I mean, you see this I here. I'm going to take all of these intervals and just cycle through them from 1 all the way to 9. And for each interval, so for 1, 2, 3, 4, all the way to 9, I'm going to take the position at that interval and subtract the position at the previous interval. So for I equals 1, I'm going to take the position at I equals 1 and then subtract the position at I equals 0. And then I'm going to divide that by the time at the current interval minus the time at the previous interval. So what this is I'm taking the change in position and I'm dividing it by the change in time. So that would give me the velocity for each interval. So that's the average velocity. The total velocity is the position at the current interval minus the initial position divided by the time at the current interval minus the initial time. So instead of the velocity within each time interval, it's the velocity between the very beginning and the current point. So that's what the difference is there. So moving forward to calculating the acceleration from the velocity, we're going to use the average velocity here because that's going to be much more accurate because you did the calculation over a shorter time interval. Usually the calculations done over shorter time intervals are going to be the most accurate. So moving on to acceleration, we do the same thing. We set up arrays to hold our data once we calculate it. We loop through the intervals between 1 and 9. And for each one, we calculate the average acceleration, which would be the acceleration between the current interval and the previous one. And then we calculate the total acceleration, which is the acceleration between the current interval and the very beginning. So hopefully that cleared up what that question meant. If you still have questions, please feel free to contact any member of the teaching staff and we'll help you. The final thing this notebook does is it just takes all of the data that was calculated and given and it plots it in a nice neat chart. It may also be helpful if you're sort of a visual learner, if you like to see graphs to plot this. You can plot all of this data in a very similar manner to this was plotted. Just change the argument x here to either the velocity or the acceleration or whichever you like. So that's how to do the numerical exercise here. All of these sort of concepts are going to keep coming back over and over again. So if you have any questions, please feel free to contact myself, Morton, or Jeremy, and we'll do our best to clear things up.